All right, welcome, people. I I'm gonna go through Unit 5 at least for now. Just recap everything that we've done. I'm gonna try and do it per presentations that we have done, so that if you are at home and you want to study, then you can listen to me yap about it rather than ChatGPT, and I think that's better. So, on today's menu, energy recap. So this is all we did in class, but people don't listen, right? So we're gonna do it again, but then here. One, energy recap, checking in what energy is, what you should already know from MYP3, what it is, what the units are, what the definition is, what we can think about. Then we're going to talk about heat versus temperature. What is the difference? Because no, they ain't the same. They are not the same. They are severely different. And we're going to be able to define that difference. Then we're going to see how heat is transferred in liquid versus solid, liquid and gas, I should say. Bang. Because those are the same and it does so differently in solid. And then we're going to finish it off with the heat curve that you should know should look like a little bit like this, if you remember correctly. Okay, let's start at the start with an energy recap. Bang, different area. Okay, so an energy recap, we should know quite a bit that energy, the unit that we give for energy, all types of energy, is in joules. This is a J, so joules. And you can have different forms of energy. We should know quite a bit of these. One of them is thermal, so that's like the fires, heat, na. Another one that we know easily is like kinetic motion, which is the energy of, kinetic energy, which is the energy of motion. And there's many others, such as chemical inside of batteries. We have chemical bonds that contain a lot of energy. Maybe gravitational, think about Isaac, Mr. Newton, who had like a little apple fall on his head, stuff like that. Those are different forms of energy, and we express these in joules. What do we need to know further about energy? How can we give a definition to this? At least what we do and how it's done in the book is that energy is the ability to do work. Ability to do work. And what is work precisely? It is enact any kind of change. So for example, think about electricity, electric energy flowing through your wires and your screen right now, and turning that electric energy into, for example, sound energy as well as light energy that you can see. And this is what we call work. That transformation from electrical energy into different forms of energy, that is work. So energy is defined as the ability to do work. Same as if I have a stick with two ends on it, apparently, and then you drop it, we have gravitational potential energy up here. We drop it, I catch it in my hand, and whilst it's falling, we have kinetic energy. These changes is what work is. So work is change. That should be in your brains already from last year. Energy in joules, different forms of energy, and it's defined as the ability to do work, which is changing one energy form into another. So transformation of energy. What we should also know about energy is that we cannot create it and we cannot destroy it. Right? Because we can only transform it. So once we have a form of energy, which in the Big Bang Theory, that bang, there was energy, but yeah, where did that come from? That's difficult. But once we have energy, let's say in your electrical wires right now, we are not creating this sound and light energy. No, we are transforming electrical energy into these different ones, right? So energy cannot be created nor destroyed, but can only be transformed, like a transformer. In that awesome. Transform. Duh. That is what we need to know. Cool. Energy. Yippee. Let's go on then to heat and temperature, because there is a difference between it. Heat, I'll go to later because that's a bit more difficult. Temperature, we are more temperature. We are more familiar with. That says temperature, by the way. Let me check if I think it's working. Okay. Heat versus temperature. Temperature is quite easy because this we just measure, for example, in Celsius or Fahrenheit or Kelvin. And it is, definition, bang, the average kinetic energy of particles. Yep. So temperature is the average kinetic energy of particles. If we have a particle here and this guy is not moving much, that means it has a low amount of movement and thus a low temperature. If we then have this little slow, sad particle and we heat it up with a forest fire or whatever fire, we give it energy, what's going to happen? It's going to start moving more rapidly. This means that it has now a higher temperature. So temperature is the average kinetic energy of particles, and that is temperature. And we measure this in Celsius often, sometimes Kelvin, or if you're really crazy, Fahrenheit. That is temperature. So this is something that you can easily relate to, I hope. And in particle theory, we say that average kinetic energy of particles is temperature, the speed of which particles move. So if you have a little ice cube that you just took out of the freezer, you know that the particles inside of this are moving very slowly because what? They have around 0 degrees Celsius. If we then let that turn into a puddle of water, these molecules in it now are hotter, and so they are moving more quickly around the place. And that means that it's hotter. That is temperature. Heat, however, is something different. This is, let me write it, it's the total amount of energy transferred between two different objects. Transferred between objects. Bada bing, bada bang. And this is our energy. So this unit, we have joules. Yes? So this means how much heat energy is transferred between two things. So for example, if I have Gojo over here and I pour boiling hot water on him, he is going to get heat transferred onto him from that 100 degrees boiling water onto his 37 degree body. That is heat transfer energy. And here we have the temperatures of those two things, of the water and of Gojo. Yeah? And heat is when this starts touching Gojo, then heat is transferred. The energy from the water is transferred to Gojo. And we'll get into how exactly that happens in a little bit. So you can then also ask the question, if you have a fire and you have these little sparks flying around, let's say these sparks are 500 degrees each. Let's say this tiny little spark lands on your hand, or I get a big water cooker and I have 1 liter, 1 liter of 100 degrees water, and I pour that on you. Which one would you rather have poured on you? One little tiny particle that is a higher temperature, or 1 whole liter of lower temperature? I assume you're going to say, I'd rather have this. Oh, excuse me. Of course not, unless you're a masochist. I'd rather have this tiny little particle, even though it's super hot. I won't actually feel it. And why is that? Because the total amount of heat transferred is not that large. It is a tiny little speck, so the heat cannot be transferred that much. Whilst if I have 1 liter of water, there's a lot of heat within that. So this dude has a higher temperature, and this dude has a higher amount of heat. Coolio. That is heat versus temperature. Then, how do we actually have this transferal? How does heat get transferred in liquids, and how does it happen in solids? So in liquids and gases, so this is liquid and gas, all these particles can flow freely. I assume that you can maybe have a water ball next to you, and if you're kind of shaky, you see that these all the particles within it that you can't really see, but you see that everything can move pretty clearly and freely. And there you go, some audio ASMR. The same with gas around us. It's constantly moving. It's free to go anywhere they please. So these particles are just moving around. Let's say we have one particle here that's moving at an incredible speed. It's going, it's zooming. Then we know that it has a high temperature because it's going fast. And let's say we have a cold little loser here that is not moving at all. So we have it as a low temperature. How does heat transferal work? So heat, how does that transferal work in liquids and gases is that this fast particle, it's moving around the place, going here, there, and eventually it will bump into another particle. If that particle here, for example, is colder, what's going to happen? It's going to bounce into it and give it some of its energy. If you can imagine, that particle is now going to start bouncing away from it. So part of the energy, part of the heat from this particle that was very high temperature is given to the low temperature one. So this guy is now going to start moving relatively more quickly. So the temperature of this particle goes up, and this guy gave some of that energy to him. So his temperature relatively will go down a little bit, even though he's still fast. So this is how it works in liquid and gases. Just imagine you have a room or a bottle or whatever, and there's a lot of particles within it, and they are constantly on the move. And at some point, they will bounce into each other, and when they do, they just give a little bit of energy to someone. They get slower, aka lower temperature, and the one they bump into gets faster. You can also think about this. Let's imagine you're in a classroom, you're running around like a lunatic, and you bounce into one of your friends. They go flying, so they have a higher kinetic energy, aka temperature, and you slow down because you bumped into someone. That is how it works in liquids and gases. Fast particles, high temperature, bounce into other particles and give some of their energy to it. Yes? That is how it works in liquids and gases. How does it work then in a solid? Because a solid, it looks a little bit different. Solids are not free to move like your water. Maybe you have a desk right in front of you. That one's not melting away because it is solid. And that is because the particles are very close to each other. And they cannot move freely. So if we have a room here, there's just going to be, let's say we have an iron ingot. They're not going to be flowing around the place like we have here with liquids and gases. They're stuck inside this small little space with each other. Now, what happens? Can I do colors? Highlighter? Maybe. This is for another day. But how does it work within solids? Is we have the same concept of a fast particle has a high temperature if it's moving fast, and if it is moving slowly, it has a low temperature. But here they can't really move. So how we say this kinetic energy within solids is that they vibrate back and forth. They're constantly like vibrating as if they're, I don't know, they had too many Red Bulls, right? They're shaking, they're shaking, they're shaking. So all of these are kind of trembling around with each other. So imagine all of them are kind of trembling together, like, right? And if you are warmer, that trembling is going to be more. So you're going to be trembling more. Okay, so let's say we have our little piece of metal here, and I'm going to add some fire, highly realistically drawn here. So this guy was just, jittering a little bit, but now it's getting hotter. And if we know, heat, temperature means that you are moving more quickly. So it's going to start bouncing like an absolute maniac. This one's going to start vibrating more because it has more kinetic energy and thus a higher temperature. Now you can imagine this guy next to him, the particle next to him, is getting bumped into a lot. So this guy will get part of that kinetic energy and also start moving like a madman. Same with this guy. This guy's going to start moving like a madman too. Now these are also moving like crazy, and so their neighbors are constantly getting bumped into, and so they're going to start moving like maniacs too. And as time progresses, all of these are going to be moving like crazy. So the heat will be transferred from here to here, and then over and over and over and over and over. And then the entire metal gets hot. You can maybe also envision this if you're sitting close to someone in the classroom and they read that they got an 8 for their exam, they're going to start going crazy, right? They're going to go, they bounce into you, and you will also start moving. And so if you connect that to being temperature, if they start moving, aka they start getting hotter, they bounce into you, and you will also then be bounced with them. And if there's someone next to you, you bounce into them, and they're going to also start bouncing. So that is how heat is transferred in liquids and in solids. Another classic question that you can get asked is then, okay, I'm going to pour some boiling water in here. It's going to be giga hot. How then does the energy and heat eventually get out of this cup? We can then just zoom into these different places. Hot water means we have giga fast particles moving around, right? So these particles are moving very, very quickly. And if we zoom into this barrier here, it's going to look something like this. We have our wall of the cup, and in that cup, we have our solid. So they're all nice and cozy next to each other. And for now, nothing's happening. Then we pour in that boiling water. And so what's going to happen? There's going to be a lot of fast particles that are constantly bouncing into and off of this wall. So these fast particles are going to give some of their kinetic energy. They're going to bounce into these particles. So these are going to start jittering. These get hotter and hotter and hotter, a higher temperature because they are jittering. And now again, if we look back here, if these ones jitter, the ones next to it start jittering. So this jitters, then this guy over there is going to start going crazy. This guy goes crazy up until the edge of the wall. Right? Now the edge of the wall has particles that are moving like crazy. This is more zoomed in than the other one. Eventually, here now we have these crazy, crazy, crazy particles. And now we have the cold, sweet air that is slow and slow. But if you bump into this cup now, you're going to bump into someone that is vibrating like a maniac. And so it's going to come here, it's going to get bounced away like crazy. Not like crazy, but it's going to have more kinetic energy, and so it is going to be hotter. And let's say we then feel with our hand, there we go. We feel with our hand these fast particles. What do we feel? That it's warm, right? Because these particles are moving so quickly. Awesome, sawsome. So that is the combination of a liquid into solid. And we can say the same about Gojo over here. That water has these fast moving particles that is bouncing against his limitless border, but let's say he put it off. So into his skin, these start jittering, and that's why he feels warm. And his temperature is going to increase. Cool. Then, last part. This one's kind of a tough part. I don't know how long I've been going, but that's life. We have heat curves. And heat curves show us the relation between the temperature increase, so the speed of particles, and the heat in a system, so the amount of energy put in. Now, I'm going to draw it for water because I think that's the easiest. And we have two important points for water. One is when it starts melting, and I hope we know that that is 0 degrees. Here, you're either melting, aka from ice to water, or you are freezing. And that means that you're going from water to ice. And up here at a 100 degrees, we are going to be boiling, or we are going to be condensating. I hope that was correct. I think so. How do these charts look? What we can assume is this is increasing, right, as we go. What this means, basically, if we go over this way on our graph, that means that there's more heat being put into the system, aka more fire, right? We have boiling water, we have an ice cube here, and we're putting fire on it. And the farther we go to the right, the longer that fire has been on, and the more energy it has been giving to our ice cube or water or whatever stage it is at. So if we put on the fire, we can imagine that, let's say we start at minus 10 degrees out of a cool freezer. Our temperature is going to go up as we increase that fire, right? The heat goes up because we have a fire on. There's heat transfer, and the temperature of the ice goes up until 0 degrees Celsius. And what happens then, instead of going straight up, we see a plateau. This plateau is there for a reason. What does this mean? Okay, let's have a look. We can see that temperature is not increasing, right? So we have ice here, and it's at 0 degrees, and the temperature is not moving. So here we are at 0 degrees, and also here we are at 0 degrees. Nothing's changing. But we are moving to the right on this graph, which means we increase the amount of heat. So the fire has been on. The fire has been on all this time. I don't know what, this is an awful fire. The fire has been on, but the ice is still ice, and it's 0 degrees. So how is this explained? It is because if we would zoom into the ice at this stage, we see that it is undergoing a process. It is currently solid, and in this solid structure, if we draw out H2O, this is not a professional drawing, but I hope it gets the point across. There's all these water particles in our ice, and they're being held together by these very strong bonds. Okay? And as we increase the fire on this, in this plateau, our temperature is not increasing, so these H2O particles, they're not moving faster because they're still at 0 degrees. What's happening with this increased amount of heat? We are breaking away these bonds. That is what our heat is doing. Oh, there goes my O. Yeah? That is what's happening over here. We are breaking the bonds. We are breaking the bonds within the ice. And once we break these bonds, guess what? These particles are now looser and thus can move around and are a liquid. That is what's happening at these plateaus. Okay? We have a plateau because we are breaking the bonds within the ice. Coolio. Then, at some point, we turn into water, what we have right here. And in this water, we are now free to go up once again. Right? We increase the fire, and if you put some boiling water, some water onto your fire stove, you put on the fire, that temperature is going to skyrocket up, depending on the degree and the power of your stove. But the temperature is going to go up, and eventually it's going to start bubbling. And here again, I hope we can see the pattern now. It's going to plateau again. And why is that? Because here we are at a liquid. We are at water liquid. Here we are at ice, right? At this part. And now up here, we have arrived at a gaseous state. The water is now boiling, and over here, we are gas. So again, same principle. Here at 100 degrees water, we have still some bonds within the water. It's weaker than here. And as you can imagine, we are again breaking the bonds of the water. And that is where our heat is going. The heat is not increasing temperature. We're always at 100 degrees here. The heat energy is being put into breaking our bonds within the water. Because the water particles can move freely, but every now and then they will come close enough and they have a weak little interaction here. And that interaction is being broken. And once that's completely broken, guess what? This particle right here, our little H2O, is free to float and become gas. Yes? And that is what's happening here. The bonds in the water are being broken. And only once they have been broken will the heat again increase temperature. Bada bing, bada bang. That one's a bit difficult though. So, yeah. Let me know if you have any questions about that. Where's my goals? Anyway. Okay, I have no clue where it is. Here it is. So, we did our energy recap. We did heat versus temperature, heat transferred in liquid versus solid, and then our heat curves over here with two plateaus. So both these plateaus, just to remind you, if the explanation was a bit difficult, this is for breaking our bonds. That is where our energy is going. Why do we plateau? Because temperature doesn't increase because of the heat here, because all of the energy from the heat is being put into breaking our ice bonds or breaking our water bonds. All right. Enjoy that. Bye. Bye. Bye.